about the second lab, which is lines of charge. So just an introduction, the purpose of the lab, similar to lab one, is to observe how charged objects interact with each other and its surroundings in a natural setting. An overview of the lab procedure is that in this lab, we will be using the quantitative data that we gathered in lab one, and we will be using a GlowScripts model to use a more accurate approach to determine the charge of each piece of tape. So shown in the diagram right here, in lab one, we model the tape as a point charge. In lab two, we will model the tape as an evenly distributed charges on the surface of the tape. So the concepts that we're using is Coulomb's law, which we're using to find the electric force by multiplying the electric field times the charge. And we're also using the superposition for distributed charges concept, in which we're dividing the tape into small segments, and then we're finding the electric field for the small segments, and then we're calculating the net electric field by summing all of those individual electric fields. And we're also using Newton's second law, in which when we measure when the top tape is floating from the bottom tape, that distance, the forces are equal. So that means the gravitational force should be equal to the electric force. Some quantitative data is that the length of the tape is 0.2 meters, the weight is 0.0002 kilograms, the distance was found to be 1.6 centimeters for floating, some constant k, and the charge of one electron. The lab result for the charge of tape was 5.9 times 10 to the negative 8 coulombs. So just an overview of the results. In the model diagram, the green arrows represent the electric field for each separated particle within the tape. The white arrow shows the electric force, and the yellow arrow shows the gravitational force. And using this model, the charge of the tape was determined to be 6.112 times 10 to the negative 9 coulombs. Um, and this is very different from the calculated charge that was found in lab 1, which is way higher than the value found in lab 2, but I will talk about that more later. Just the model, I inserted the quantitative value for the mass, and then just a placeholder for the charge right now, but I'll be changing that to fit the model where the electric force equals the gravitational force. And then I copied the electric field formula that we had in lab 0. I'm also lab 1. So the first function in this picture, we didn't have to do anything about it because we were provided, but it basically models the tape as the line charge. And then I edited the y vector component of the top charge to model the 16 centimeters of the floating distance. And then basically here I adjusted the scales for the arrow just depending on the model to see a visual aspect and see which one fit the best. And then in the iteration for loop, which is the very important part, what I'm basically doing is I'm iterating through each individual separated piece of tape that I have, and the n is 20 in my case. So I'm finding the electric field for each part, and then I'm multiplying the electric field by the charge to find the electric force, and then I'm summing it at the ends to find the net electric force, sorry. And then some assumptions I used in the model is that I ignored air resistance, the factor of the tape, and then I treated the tapes as evenly distributed charge models similar to a rod, and then I assumed that the two tapes had equal mass and charge. So just looking at the reflection questions that were provided, the first one has to compare the estimated value of the charge when I used lab 1 as a point charge versus lab 2 when I used the line charge model. So I used the percent error to see like how drastic of a difference it was. And as you can see, the difference was very high of 865% error, with the line charge model being way smaller than the point charge model. And the second question asks, why do these estimates differ? And I said that the point charge model is not an accurate representation of the tape, which is 20 centimeters. It's not really valid or accurate to model a long piece of tape to just one point charge. Versus in lab 2, we modeled the tape charge to what it's more likely in real nature. So evenly distributed charges on the surface of the tape. So I concluded that that's the charge that we found in lab 2 is way closer to the model. And this is because as n increases, or the number of separated parts on the tape, it approaches the real value of the tape as kind of like an asymptote. So I use n as 20 in my lab, but as n approaches infinity, then it will approach the real charge of the tank. So yeah, thanks for listening.